Hey y'all, welcome back. Today we are going to start a new unit on what are known as parametric equations. So we are going to look at what parametric equations are, how to graph them, how to solve certain problems using parametric equations, and also we'll look at some applications in this unit. Now today we're just going to focus on sort of explaining what a set of parametric equations is, and also look at how you might sketch a graph. So let's first try to explain what a parametric equation is. So up to this point, when you've graphed equations, you've usually just used a single equation with two variables, right, x and y. We saw some cases, down the line of systems of equations where you have multiple equations, but even in those, you're still just using two variables. In this unit, you're going to look at situations where you're going to find that it's useful to have a third variable. And we call that third variable the parameter, thus parametric equations. So let's dive in and let me give you an example of why you would even want to integrate a third variable into these graphs. So consider the path of an object that's propelled in the air at a 45-degree angle, and we write an equation to model the path of that object. So this equation could be used to model the path of an object that gets launched from the ground and then lands somewhere about 70 some odd feet away. If you look at this, we can get some information if we let the y-axis represent height and the x-axis represent distance. We can see that the object landed 72, we'll say, feet away. We can say that the object reached a maximum height of 18 feet, and that happened about 36 feet away, or actually exactly 36 feet away. But there's one big piece of information that this function does not give us. Okay, this equation does not tell the whole story. Although it does tell you where the object has been, and we can find lots of locations, right? Like 20 feet away from where it was launched, it was about, let's see here, about 14.5 feet above the ground, right? So it can tell you where the object was, but it does not tell you when the object was at any given point. There's no information here about how long it took the object to go to the maximum height and get back down. So that's to determine this time that we would want to know about, we can introduce a third variable. Typically we use t, and we call that the parameter, like I was talking about earlier. It is possible to write a set of equations for both x and y in terms of t, or as a function of t, to obtain parametric equations that will model this exact same behavior and give us the same information about where the object was, but also give us information about when it was at any given point. Now, there are a lot of different ways to write these parametric equations, and there are actually, depending on how you define your parameter, several different parametric equations that will produce this same graph, but that might have different times associated with it. So I'm not going to get into how to come up with these parametric equations quite yet, but let me show you an example of a set of parametric equations that will show you this same behavior, but also give you information about the time. So let's say we wanted x to be represented, like normally you would write like x equals, but I'm going to actually, the way Desmos works here, I'm going to write it as a set of coordinates. So x is going to equal 24 times the square root of 2 times t. So that's x. We would write it as like x equals, and then the y would be negative 16 t squared plus 24 times the square root of 2 times t. Now I know those equations look, there's kind of a lot going on there. The ones we're going to look at are going to be a little simpler than that. I just wanted to show you a quick example of why parametric equations are useful. So here, notice that the time is not, there is a domain restriction on the time here. This particular software has us defaulted from 0 to 1, meaning like at 0 seconds we're here, and at 1 second we're here. So we can modify this to get an idea of what time the object reached every individual point. Like if I increase that upper limit of the domain restriction, I can, let's say 2 seconds it gets there, 3 seconds a little further, so it kind of hits ground, it looks like at about 2.1 or 2.2, well, maybe a little bit in between there. Let's get a little, we'll get pretty close here. So it looks like it's about 2.1 seconds until it hits the ground, and we can find the time it takes to reach any particular point on here. If I divide, let's divide that in half and do like 1.05. We're getting pretty close to the maximum there. And I'm not showing you exactly how to come up with these equations, or even with these times. I'm just kind of estimating here. Later on I'll show you exactly how to find, for instance, like at what time did it reach the maximum and that sort of thing. But I just wanted to give you an example of why you would even want to use parametric equations. And really the primary use for it here is to extract extra information about, for instance, the path of an object, or maybe the spin, like the angle at which something's spinning or something like that. So we're going to get into all of this. I'm going to show you some examples of how to actually do some sketches, but I just want to give you a little intro here. So let's get into some sketches here.
So number one, let's say that an object's x position is defined by -2t, where t is just some time. And its y position is defined as 4t squared minus 4. So the x coordinate is changing linearly while the y coordinate is changing quadratically. To get kind of an idea of what this path is going to be, it's helpful to make a chart. So like if we wanted to graph this to get an idea of what this looked like, we would have our input, which is t, and then we're going to have a single output for x and a single output for y, but for each t we're going to get an ordered pair. So we're going to make a little table here where our input is t and our output consists of 2 coordinates. So let's say t is -1. Okay, so my x would be 2 and my y would be 0. Like if I plug in -1 here, -2 times -1 is 2. If I plug in -1 here, I get 4 times -1 squared, which is 1, minus 4, which is 0. So I've got this point at 2, 0, and that's occurring at t equals -1. If t is 0, then my x would be 0, and my y would be -4. So 1, 2, 3, 4. We've got a point here. This is where t is 0. What's interesting here is that from t equals -1 to t equals 0, the path, which is going to be something like this, should be indicated by a direction. So instead of just having some graph that just plots all of the coordinates that satisfy an equation, there's an actual order here. So like this would come first and then this one. If t is 1, we've got a point at -2, 0. So that would be about here. That's where t is 1. So we've got this thing coming back up, and I'm going to put a little arrow here. These arrows that I'm drawing on here are indicating the direction of the parametric curve. So we can say that whatever's object this is trying to model is going from here, down here, to back up here. If t is 2, my x is -4, and my y is 12. So it's going to be something way up here, right? Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it appears as though whatever object this is moving along a parabolic path. Now, as you can imagine, if I were to continue these t values back into further negatives, I'm going to have more points that are going to kind of be up here. If I go further along and increase the t values, my points are going to follow along this quadratic curve, or this parabolic curve. But most of the time, when you're given these parametric equations, you're given a domain restriction. And when you think about domain, usually you think of the x values being your domain. But you really want to be thinking about domain as a set of inputs. So in this case, the t values are going to consist of the domain of this overall function. So you'll usually have a domain restriction that's associated with this. So if we say that our domain is like -1 to 2 or something like that, then these would be the endpoints of the curve, and you wouldn't go anywhere beyond this. Otherwise, if you did not have that domain restriction, you might show something like this to show that it continues on, you know. But we're going to say that there actually is a domain restriction there. And what you'll see on your homework is most of these parametric equations are going to have some kind of domain restriction. So just to recap the whole domain and range issue here, this is your domain, right? These are your inputs, and then the coordinates, that is your range. So it's kind of weird here. It's not something that you're typically used to, having a range made up of multiple values for any one given input. But that's how this is going to work.
Here's another example where we have our x defined as t squared minus 4 and our y defined as 1/2 t. So I'm going to create a little table before I start plotting any points with my left-hand column being t, the parameter, and then my right-hand column I'm going to define the coordinates that I'm going to plot. And I'm going to use this domain restriction to guide which values of t I'm going to substitute in here to figure out where the points are going to go. So I'll start with -2 and move all the way to 3. Now notice on this one that -2, that t is greater than or equal to -2, but is strictly less than 3. So when we plot those points, we're going to make sure to put a closed circle on -2 and an open circle on 3, because we're not including this one in our set of points. So anyway, -2, -1, 0, 1, 2. I am going to plot that 3, even though that's not going to be part of the graph, just because I'm going to use it as an open circle and kind of use it to guide where the graph is going to go after t equals 2. So for each one of these, I'm just going to compute what the x and y coordinates are. So I'm going to start with just the x's, and then I'll work my way through the y's as well, just because sometimes it's easier to just use the same, to calculate the same equation over and over again. So we got t squared minus 4. So -2 squared minus 4 would be 4 minus 4 is 0. -1 squared would be 1 minus 4 would be -3. 0 squared is 0. Minus 4 would be -4. 1 squared is 1 minus 4 is -3. 2 squared is 4 minus 4 is 0. And 3 squared would be 9 minus 4 is 5. So those are the x coordinates. Now I'll calculate the y coordinates by doing kind of the same thing, but I'm going to use the y equation. So y is 1/2 t. So half of -2 is -1. Half of -1 is -1/2. Half of 0 is 0. Half of 1 is 1/2. Half of 2 is 1. And then finally half of 3 is 1.5, or 3 halves. So these are the coordinates I'm going to plot. And so what we need here is we need a grid. And it looks like our x's going between basically -5 and 5. So I'll just mark that. Let's see. So 1, 2, 3, 4, 5, -1, -2, -3, -4, -5. Go ahead and label those here. And then my y values don't go very far, so I'm not going to worry too much about going further than 5. It won't even need to go that far. But just to kind of square this up, I'm going to go to 5 and -5. Okay, so we're just trying to get an idea of the path of the object and when the object was at each of these coordinates. So at 0, -1, we are going to have a point 0, -1 would be right here. Oops, that is not a circle. Here we go. And so we're going to put a closed dot there. When time is -1, we're at -3, comma, -1/2, so that'd be roughly here. When time is 0, we're at -4, 0. At time equals 1, we're at -3, comma, +1/2. So you can kind of see this sideways parabola starting to be generated here. When time is 2, we've got a point 0, comma, 1. And then finally, we've got a point at 5, comma, 3/2, but I'm going to draw this one as an open circle since we're not actually including that maximum value of the domain here. So 5, comma, 1.5 is going to be about right here. And when I connect the dots here, I want to make a note of the order in which these points got plotted because I'm going to use the notation with these little arrows to show which direction the object is moving. So I'm just going to, in between each of these points, just draw little arrows here. Okay, so here is a second example, and we'll do one more. Here in example 3, we've got a sinusoidal function for x and another linear function for y. In fact, I think that's the same one. Yeah, it's the same one we had before, so that should be pretty easy to find the values for. So let's go ahead and create another table here. Keep track of what coordinates are happening when. So we've got t, we've got x, comma, y. So the t's here are going to go from 0 to 4. 0, 1, 2, 3, 4. Just a quick little note, when you see this bracket, we do want to include that point. So we're going to do a closed dot there. But with the parentheses, we're saying we want the set to go all the way up to 4, but not including 4. So we're going to indicate that with the open circle, just like we kind of did with this last one, the closed and the open circles. So now we're going to evaluate each one of these. We are going to need to compute some sinusoidal values. So I'm going to pull up the unit circle to help us do that. So let's see here. We've got at 0, sine of 0 pi over 2, so that's just sine of 0 is going to be 0. Sine of 1 pi over 2 is going to be 1. Sine of 2 pi over 2, that would be just sine of pi, that would be 0. Sine of 3 pi over 2 would be -1. Sine of 4 pi over 2 would be equivalent to sine of 2 pi, and so we're back at 0. And I'm getting all these values by looking at the unit circle and reporting back the y coordinate at those particular angle measures. The y value is just 1/2 of t, so 1/2 of 0 is still 0. 1/2 of 1 is 1/2. 1/2 of 0 is 0. 1/2 of -1 is -1/2. And 1/2 of 4 is 2. Oh, oops. Let's back that up a little bit. We're supposed to be taking 1/2 of the t value, not the x value. I got off there. So, sorry. 1/2 of 0 is 0. 1/2 of 1 is a half. 1/2 of 2 is 1. There we go. 1/2 of 3 is 1.5, or 3/2. And then 1/2 of 4 is 2. So here's our coordinates. This is supposed to be a 3 right here. This is like 1.5. And now we want to plot all these. So let me go ahead and hide that unit circle. We don't need that. Here we go. So let's go ahead and plot these out. Let's see, we definitely have 0, 0. So this doesn't go very far, so I'm going to make my units, I'm going to put a little bit of space in between my units here. So here's 1, 2, 1, 2, -1, -2, and then finally -1, -2 going this way.
Here's my x, here's my y. Okay, so now we're going to plot our points and just keep track of the direction that we're moving in. So we're going to start at the origin, 0, 0. We're going to go to 1, 1/2. Then 0, 1. Then -1, 3/2. And then 0, 2. So let's see here. We're going... Now hold on here. Is that right? I feel like we missed something here, but maybe not. Yeah, okay, so we started at 0, 0. We went from that to 1, 1/2. Then from there we went to -1, 3/2. Okay. And then something does just not seem right here. What is going on? Oh, wait, I see my mistake here. I'm trying to work this a little too fast here. This point right here is in the wrong spot. So yeah, let's try that again. We've got 0, 0, we've got 1, 1/2, then 0, 1, then -1, 3/2, which would be up here. This is going to look much better. And then 0, 2. So yeah, so our graph is going to do something like this, which is going to look like kind of a sinusoidal path here. The only thing I need to fix as well is the fact that this point right here should be an open circle. So let me redraw that one. Right here should be open. So you can see that we start here at 0, 0, and then the object kind of curves around in a sinusoidal path until we get to 0, 2.
So there you go. There's a couple of examples of how to graph parametric equations. I hope that it clarified things a little bit. But if you have any questions at all, please reach out to me and I will help you with anything that you need. So that's pretty much it for today, and I'll see you next time.